Welcome to part 3 on this foot on wheels problem in this recitation of optimization using spreadsheets for advanced network design. If you haven't yet, as we usually do, please pause the video, read through the problem statement, identify all key data points, and be back to us in a few minutes so that we can work through it together. Awesome. So in this case, we have 3 more halves into the model. As you read through, you will see that we have the possibility of renting only one of these 3 additional halves we're exploring. So this is to analyze the potential strategy. We can still use the existing half in the model. So the idea here is to say, okay, I do have 3 halves and I'm going to use them as I need it, only and as our model suggests us to use them. But I will rent one more half. So I need to add all these 3 to the equation, to the model formulation, and I will analyze out of the 3 of them, if I need to use one, which one would I use? Of course, we're receiving additional information in terms of the delivery time in minutes and the capacity so that this is aligned with the original model we have in part 2, including the other 3 halves. So let's go directly to question 1. So we still have the exact same model we had in part 2. So let's guess that we'll still continue to have objective function, demand, capacity constraint, conservation of flow, and non-negativity constraint. But what we are going to add here is a different element. In order to identify which of the halves are operating or not in our model and to limit that to be 1 as expected, because we're not just told we're renting any of the halves no matter the capacity or the flow that's going through them. No, what being told that we have the chance to rent only 1. So to do so, we're going to add 2 more elements to our model. The first one is the binary variables. To force the model, make a variable 1 if the half is rented and 0 if it's not. And we're also going to use a linking constraint. As you probably learned from the lectures, the linking constraint is going to allow us to link our objective function with all the variables and flows, including this binary variable we're incorporating into the model. So with this, I invite you to select everything we have talked about: binary variable, objective, demand, linking constraint, conservation of flow, capacity constraint, and non-negativity constraint. Submit your answer. Go to question 2, double check what we're being asked, and meet me back in the spreadsheets in a few minutes so that we work through it together. Remember that if you still have any questions about the question 1 answer, you're welcome to click the show answer button, find further details there, or use the discussion forum to discuss about it together. Awesome. To start solving this, let's first start by duplicating, as we like to do, our tab so that we have part 3 here and we don't overwrite everything. And let's bring all the information we have from halves 4, 5, and 6 to our spreadsheet. So the first 3 elements we're including are in the minutes between the central kitchen to the halves. So this is going to be 5, 6, and 4. And we can also bring the capacity from those, which is 200 for each one of them. I'll just replicate the format. And then I'm going to do the same for the minutes for the outbound network. As this is going to bring me the areas in the way I'm copy pasting, I'll bring it here. Then I'm just bringing it to my table. I don't need this anymore, so I'm good to go. I'll do some formatting so that it's clear to me. Remember, this has to be easy to read for you. So I encourage to work this way. So we have all the new data points here. We have the new inbound number of minutes, the new capacity, the new outbound number of minutes. We're ready to go to maximize the view of our spreadsheet and continue to adjust our model. Since we adjusted the arrays we're using for our inbound and outbound number of minutes. We also need to adjust the array of variables we're using. So I'm going to add my 3 halves here, and this is what I'm doing so that I complete the names. I also need to drag and drop, and I would say recalculate my calculated fields. You can see here that it's already adding all the halves, but just double check because it depends on how you added those columns, if it's continued to add up all the halves, or you will need to adjust that calculated field. I should be good to go in terms of the flows to compare with the demand. I'm good to go in terms of the flows to compare both with the hub capacity and with the inbound, so that I use my conservation of flow. What I'm missing is my binary variables to determine how many rented halves I want to have, and also my linking constraint. So first, let's do the binary variables. I'm going to just write rented here. I'll just highlight this in color for me, and I will copy paste the color coding so to know that these are variables. And then the next one I need to work on is the linking constraint. Remember that in the linking constraint I need a large enough number, so I'm going to do m equal the sum of all demand. You probably remember that from the lecture. If not, I invite you to return to the lecture, go again through the slides. You will find the formula of the linking constraint and a great explanation and the m as a large enough number for the linking constraint to work. And another data point you can have here, in case you want to then play with different scenarios, I would just say max number of rented halves that we allow, and we can just make this 1. I'm going to highlight this as a provided data, and this is the calculated field for color coding purposes. Let's build my linking constraint. As you know, the linking constraint is going to be the number of units flowing from that certain facility minus the binary variable that it's on N15 for me, times the large enough number. I'm going to fix that so I can drag and drop my formula. I'll go for it. As you know, we need to make the linking constraint lower or equal to 0, right? And let's see how that works and what happens when it's not. If we don't have the linking constraint and we have 10 units flowing from central kitchen to hub 4, just think of us not still using the linking constraint. Then the model will have no need to turn the binary variable into 1 because there's nothing saying that the linking constraint cannot be 10 in this case. With that, the model will be able to use any of the rented hub, because I'm not telling the model only use 1, because I cannot have this activated binary variables that tell me, hey, there are 3 halves rented in this model. So what I'm going to do is use a linking constraint, make it lower or equal to 0, which will force this rented to become 1. And as you can see, as soon as the rented hub become 1, because it has a flow, it's minus a number. Okay, it's below 0. So this is fulfilling the constraint. Linking constraint is lower or equal to 0. As you can see, this applies also when there's no flow. If there's no flow, I need this to be 0. So the model will just keep it as is. It's minimizing time. It's not necessary to send any more units. If there are no units flowing, this is not going to change, and I will remain having a 0 here in the rented binary variable, and the model will be operating as we need it, so that at the end of the day, I can sum all the rented halves and tell the model, please make sure that this is always 1, right? Because that's the maximum number of rented halves I'm allowing. I'll highlight this and color code it as calculated field so that we have that handy. And I will just make this 0 to avoid any confusions. And I'm ready to go to fix my objective function and then do the solver parameters. You can see I have troubles with both my inbound and outbound calculations. Why is that? Because we added more halves to the equation that were not there in the first place. So on the first array, I just fixed it. On the second one, because of the way I added the columns, it already included those, so no need to change. Now I'll do the same for the outbound, including all new halves information. I'm all set with both arrays. So that means I should be good to go, and I'll set the solver. Okay, once again, objective function, same position, still minimizing. We still have a different array of variables, a larger one for inbound and outbound, but also a new binary variable array. So I'm going to delete this and add all the new ones. Remember to separate them using a comma. And I'm all set with that. I'm going to adjust the existing constraints just to make sure I'm considering all halves now. So I'm going to change the first one. The first one is the conservation of flow constraint. It looks good. It already considers everything going inside all the halves and outside from all the halves. So that's fine, no need to change it. The next one is the non-negativity constraint. For me, it's still considering all 6 because of the way I extended my table. So keep that in mind. If you didn't do it the same way I did, you need to change this array to include all halves. For me, it has worked perfectly. The next one, let's find it. This one is the capacity constraint. So this is telling me that the flow from all the halves or to all the halves, which is the same as you know, cannot be larger than the capacity. So I'm going to change this to include all 6 halves. That's perfect. And the next one, and it was the last but not least that we have to adjust, is the demand constraint. Demand constraint looks good, right? Because it says that the flow to all areas is larger or equal to the constraint, that is the demand from all those areas. That information is still in the same location, so no changes are needed. With that, we have reviewed all our constraints, our existing ones. Remember, we added a couple more, so this is yet to be done. But we have just made sure that we are still working with the constraints we had in the previous part of the problem, but now including all the new halves, and let's add the new constraints. So the first one is saying, okay, all these 3 should be binary because we only allow ones or zeros, right? The next one is going to be all this should be lower or equal to 0. We talked already about the linking constraint. If you still are not that sure, please pause the video, go back to the lecture, or revisit what we have just done and talk about, or of course use the discussion forum for the further support of our CTAs. Last but not least, we need to tell the model that we can only rent one half. Of course, probably because we cannot afford more than one, or we think it's not going to be the best choice for our company. So I'll just click OK. And I'm good to go. I'll click solve and I'm going to find my results. Use that to populate your answers to identify which of the halves should be rented. As you can see here, I'm personally renting half 5. I'm going to use it to deliver 101 units from the central kitchen to the areas. I'm going to deliver those to area 3, as you can see here. And this is going to take 4,050 minutes from our company. Good luck with your answer. If you didn't receive the same outcome I got from my model, Double check all your inputs, double check your objective function, your calculated fields. Go back to your solver settings and analyze each one of the constraints. And if you still have any questions, please use the discussion forum for further support. See you in the next and last part of this problem, and hopefully you stay with us to the end so we can talk about the insights from the information we're receiving.